Hey guys, how's it going? Let me get everything set up here. All right, good. Hey, how are you? Hopefully everything's going good with you guys today. Um, I'm doing all right. Did a bunch of yard work today, um, so that's fun. And now it's time to help you guys with some questions. Um, my plan is just to go through questions like I usually do. But if you have specific questions, definitely let me know and I can help you out with those. So that is kind of the way this goes. I figured the first thing I do, I have copy of the questions from the back of our book, and I was just going to kind of read through these, and if I saw one that was interesting, I could go through and do it real quick. Um, this is one that I found that was interesting. So this is going to be more for pre-AP people, but if you are AP, then this should be a good reminder. Okay, so number 5 here. You may have noticed that when water boils, you see bubbles that rise to the surface of the water. I think we've all seen water boil. What is inside of these bubbles? Air, hydrogen and oxygen gas, water vapor, carbon dioxide gas. Okay, so think about it. What is actually happening when you boil water? All you're doing is taking that water, increasing it past 100 degrees, and that turns the water from a liquid to a gas. So that's going to be gaseous water in there. It's not splitting. It's not turning into hydrogen and oxygen gas, both of which are very flammable. If we did that every time we would boil water, we would probably blow up our houses. So that's not what's happening. Um, and then carbon dioxide gas, no, there's no carbon in water, H2O. And air is just a crazy mixture of a lot of things, oxygen and nitrogen being the two big uns, carbon dioxide as well. But then a lot of other little stuff that's just kind of barely there. So not air, because all of those things can't be found in water. To a degree. That's overcomplicating things. All right, so that's one thing you might want to think about. This is a good example of, you know, you can always be studying chemistry. All right, if you see water boiling because you're making spaghetti or something, think about it. What's happening to that water there? Why is it that when you boil spaghetti, it becomes soft and pliable and not hard and straight? It's things that chemistry is how things work and you do things in the world. So chemistry can explain a good portion of it. So think about it. Okay, is boiling water a chemical or physical change? Explain. We are defining it as a physical change because there are no bonds being broken, no bonds being made. For you AP people out there, you'll learn that is, while true, it's not the whole story. We'll get into intermolecular forces later on. You do break and make intermolecular forces when you boil water. Okay. All right, let's see here. So that's about, this is all, here we go. Sketch a magnified view showing atoms, molecules of each of the following and explain. A heterogeneous mixture of two different compounds. All right. So let me pull something up real quick. I need something to write on. Allow me to get something to write on. There we go. All right. So to draw a thing, I'm going to draw a container. This is going to be a heterogeneous mixture of two different compounds. So for that, remember, heterogeneous just means that there are clumps of it, that it's not well mixed. So I can go through and draw a bunch of stuff over here. This is my atoms. They're beautiful. Look at them go. Some of them look like backward sixes. Okay, there's that. And this is going to be my first substance. My second substance is going to be here. And there it is. This is heterogeneous because there's a big clump. They are separated. If I wanted to make this a little bit more complicated, I could go back and draw even more of the first stuff over here. I know it's a slightly different color, sue me. So there we go. It's the fact that these guys are separated, which makes them heterogeneous. Okay. Next one. A homogeneous mixture of an element and a compound. Ah, geez, they wanted to do compounds. So to go back, I already got rid of it. So if they're wanting compounds, they're gonna want two things together. Ah, geez. Let me redraw. So this is gonna be part one of my compound. There we go. So now these guys, it's a compound. It is two separate atom types, red and blue. So this is going to be a big clump here. And then on the other clump, is going to be green, and let's make this yellow. Okay, so it is a mixture inside the container of compounds. We have red and blue and green and yellow compounds, and they are separated. They are clumped around. So this would give you the correct answer to that. The next one was just similar, except it was just looking for an element. An element would look like this. So there's my compound, and there's my element. Were they wanting a homogeneous mixture? So that means the element has to be in here as well. There we go. So there is my homogeneous mixture with them all mixed up of a compound, the red and blue, and the green element. Element is just there by itself. Okay. All right. What else we got? What else is going on? Let's see here. There we go. So I noticed that some people are still having some problems with sig figs in pre-AP. So let's kind of run through these real quick. So this is just how many sig figs are in each of the following here. So this first one, it's so 29A is in scientific notation. In scientific notation is really easy. If you see that times 10 to the, you know that any number written in the base here is going to be significant. With scientific notation, we don't fool around putting numbers in there that aren't significant. So in this case, there's 3. In 29B, we're not able to use scientific notation trick here. So we have to go through and look. So we know these 3 here, non-zero digits, are going to be significant. So no, there's 3. We know that these leading zeros here are not significant. These just show how small something is. And then this back one could be. The rule that I'd like you to remember is that if you see a decimal point anywhere, then these back zeros are going to be significant. So in this case, we have 4 of them there. Same rules apply here with C. You have these two, definitely going to be significant. We see a decimal point, so all these back zeros count. This makes these 4. Scientific notation for D now. There's just 1 there, so 1. Just 1. E, here's a whole bunch. We see that there are a bunch of non-zeros, and then there's one non-zero that's trapped in between. Remember, those captive zeros are going to be significant as well. It's just the front and the back ones that you have to worry about. So, that case, we have 1, 2, 3, 4, 5, 6, 7. 7 sig figs on this guy. Okay. So here, we have a bunch of back zeros, but unlike before, we don't have a decimal place anywhere, which means that these guys don't count. This is just 300. Again, this is like saying it's about, 100 miles to the next city. So that's going to be, it could be 120, it could be 110, maybe 90, somewhere in there. That's kind of what we're saying here with this 300 number. Now, in this case, 301, rules state that this 0 is that captive 0. And this kind of makes sense. If I'm saying 301, you know that I measured down to that 1's place. So, in that case, all of this 10's place, the 0, you know that we measured this one as well. So, all 3 of these are going to be significant. And this guy, 300 point, we have a point, so that means all these back zeros are going to be significant. So 3 sig figs there as well. Okay. In this case, on number 33, something I've noticed in everyone's lab reports is you're missing how to actually measure these guys. So let me get this a little bit closer. Okay. So, looking at this, what significant figure can you use for this? So, let's go through and look at this. We know that this big line here is the 1's place, and these lines are going to be the 10th place. So this is going to be 0.2, 0.3, or 0.2, 0.4, 0.6, 0.8, and then there's the 4.0 on top. What can we actually measure to here? So since the measurements go to the 10th place, we could actually measure to the 100th place. So that's one way. That's something we can do there. Here, ooh, this is even better. So it looks like the big markings here are actually to the 10th place, and the small markings are to the 100th place then, which means we could actually go to the 1000th place with this graduated cylinder. This is actually a super tiny graduated cylinder. This is only 1 mil. Teeny tiny graduated cylinder. I want a tiny graduated cylinder. Someone give me a graduated cylinder for my birthday. Tiny one. All right. Okay. That's what they were asking. What is the limits of those graduated cylinders? Here, beakers show different precisions. Actually go through and label the amount of water in each of these guys. So if the markings here in this first beaker are to the 1's place, that's the only markings we have. That means we can estimate to one more, the 10th place. So in that case, looking here, I mean, I would just call this like, what, this 0.7? So 32.7. And here now the markings are on the tens place, so we can actually go to the ones place. And this looks like it's about 32. And here, this goes to the tenths place, so we can estimate to the hundredths place. And if the water's here, this is 32.7. We'll say 3. 32.73. So there's that. It looks like all of these are actually the same amount of liquid. We just changed the beaker to get more precise. So there's that. So if we label the amount of water in each with the correct number of sig figs, here we can do 2, here we can do 3, and here we can do 4. Yes, it is very possible that these beakers contain the exact same amount of water. So this is just this shows why your instruments matter so much. Which one do you think would be most expensive to buy? Probably the one on the right, because that's a super precise instrument there. It goes all the way to the thousands place. You can get more sig figs. So if we poured all of these into one container, how many sig figs could we have? In that case, and so here we would have 3, here we would have 4, and here we would have 2. So again, we don't really know. We know this is 32, but it could be, like I said, 32.8, 32.6. We can't tell that. So this is our kind of weak link here. This is going to be what we're going to round our significant figures to. So we're going to have to round it to the ones place. Remember your rules about adding and subtracting. You always find the least precise place measurement. So here we could go to the tens place. Here we did it to the ones place. Here we did it to the thousands place. And since we added them all together, we can only really say with certainty to the ones place. Okay. This is just some more math problems. Not super interesting here. We did a baby. The baby was born in a country using the metric system. I wish we used the metric system. It'd make things so much easier. Again, these are all just kind of conversion problems. If someone needs, still waiting for Sodi sub emojis. Yeah. Not partnered yet. So as soon as I get partnered, that'll happen. No, doubt it will. So although that, let me know if you guys want me to go through some more dimensional analysis stuff. I would say you need to, if you're worried about it, do what I said before. Google, converting units worksheet with key. Run through, just do like 2 problems a night. 2 problems a night should not take you more than 5 to 10 minutes to run through. And if you do that, you get used to using dimensional analysis, and it's going to help you a lot in the coming year. A lot of what we do can just be just converting units. All right, more converting unit stuff, converting temperature. That's what Google's for. Reading temperature. Where was the thing that I wanted to do? Here we go. Separation, classification, and separation of matter. So let's run through this real quick. Stretch real quick. All right. So here we have 1, 2, 3, 4, 5, 6 samples, and we can see this kind of molecular representation of them. And what we're going to do is see which ones are gaseous first. So let's go through and talk about which ones are gaseous. Well, these all look like they're particles that are filling up this entire container, right? So filling up the container, filling up the container, filling up the container, filling up the container. This one, they're packed together and they're all laying on the bottom. So it looks like gas, 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 solid, gas. All right, so those are all the gaseous compounds. Now we're going to be looking for a mixture of two gaseous elements. So remember, elements are just one type of atom in there. So it is going to be a mixture, two different elements. So here, these are all the same, but they're all the same. So that's not going to be a mixture. Mixture, 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 not a mixture. In this case, we have an element. It's something by itself, one type of atom. And this is something by itself, one type of atom. So that's two elements in a mixture. Boop, check. Here, this is a compound. A compound is something that has two types of atoms in it. So that would make this a compound. No, that's not going to be right. Here, same thing. Compound, not right. Compound, not right. So, just this guy. Even though these guys are elements, it's something that with just one type of atom. There's nothing else in here, so it's not a mixture. So for B, the only correct one would be number 6 here. Then a solid element. Okay, we only picked one solid. Or there's only one solid here, so it's pretty easy. It's just going to be number 5. Simply dimpledy. But we know the other thing you can learn from this is that this is an element. This is not a compound. It's one type of atom throughout the entire thing. All right, a mixture of a gaseous element and a gaseous compound. So this is not a compound because these two things are the same, blue and blue. Here we have a gaseous compound, blue and gold, and a gaseous element. So that works, and they're mixed together. That's good. Number 2. Here we have a gaseous compound, blue and yellow, and these guys are all elements as well because it's one type of atom by itself. So it is a mixture of a gaseous element and a gaseous compound. So that one's checked. This is just not this is not a mixture. It's all guys are all the same thing. This is a mixture, but they're, as I said before, these are both elements. So there's that. All right. Let's see here. This is fun. What's the difference between a homogeneous and heterogeneous mixture? Classify each. So a door is heterogeneous. It has like a brass metal handle or just a metal handle, aluminum, steel, I don't know. And then wood, and you can definitely see the two. The air you breathe, definitely homogeneous. It's, there's not like a clump of oxygen that's going to come in. It's always going to have like that mixture of nitrogen and oxygen. A cup of black coffee, definitely homogeneous. Good kind of homogeneous. Unfortunately, I just have a soda. Water is not a mixture. It's a pure substance. Unless they mean like the water I drink, which comes from the tap, which has, all sorts of like calcium and fluoride and all that kind of jazz in it. In which case it would be a homogeneous mixture. Salsa, definitely heterogeneous. Always got to get those, big scoop of onion. Your lab partner is going to be heterogeneous as well. Okay, there's a bunch more of these we can go through. And ooh, this is a fun one. If you have a piece of hard white blackboard chalk and heat it strongly in a flame, the mass of the piece of chalk will decrease, and eventually the chalk will crumble into a fine white dust. Does this suggest that the chalk is composed of an element or a compound? So, the question that we're being asked is this an element or a compound? And so elements, so that's going to be our goal, is to figure out, is this an element or a compound? And what we have up here is evidence of some kind of chemical reaction taking place if we heat chalk. It says at first the mass of the piece of chalk will decrease, which means that mass has to be going somewhere. It's probably going from a solid into a gas. I mean, we're essentially burning the chalk. I mean, what happens if you burn a stick? You know, it turns into ash and smoke. So that's exactly what happens here. We go through. This piece of chalk is turning into some sort of gaseous component, and a solid component is left behind. So those are two things that are happening with this. And so that means there must be something in the chalk that turns into a gas when heated, and something that turns into ash, that's fine white dust, when heated. And since we know that's the two things, that's the chalk being made up of two separate things, which means that it's a compound. It's not the same thing. Okay. This is about Shakespeare. What crap? This is in English. In Shakespeare's Richard III, the first murderer says, "Take that," and stabs Clarence. If that's not enough, I'll drown you in Malmsey butt within. Given that one butt equals 126 gallons, how many liters of Malmsey, a foul brew similar to mead, it was the unfortunate Clarence about to be drowned? All right, so this is just a fun conversion problem. So we have one butt, 126 gallons, so 126 gallons into liters. We can figure out, let's see here. Gallons to liters. It's about 3.7 liters. So for that, if we knew, what was it? Okay, so one butt is, we're trying to get to liters, right? Need to follow my own rules. We're trying to get to liters, and we know one butt equals 127 gallons. 126 gallons. And we know from here that 1 gallon is 3.78, let's say, liters. We can go about this. So let's start with liters up here. So we have 3.78 liters in 1 gallon. Now we know that 126 gallons is 1 butt. And the gallons cancel. And we know from the problem that Clarence is going to be drowned in 1 butt. 1 butt. The butts cancel. And now we have the thing set up. So at that point, we can just plug and chug. It's going to be around, what, 400 and something, 480, 460, somewhere in there. I guess I can just calculate it. It's not going to be that hard. All right. 3.78 times 1.2. Yeah, 476.28. Now we have to ask ourselves, how many sig figs are we going to use? We have this. It's a conversion. So remember, this is infinite sig figs. This is also a conversion, infinite sig figs. The only thing we have is that one but. So the one but is going to be our scientific or our significant figures, which means we only do this first one, and then we round up. So it's going to be 500 liters. One but is 500 liters. So what a time to be alive. All right. Is that? Yeah, these are all just things. Okay, here we go. Which of the following are chemical changes? Cutting food. Cutting anything is not going to lead to a chemical reaction. So, no, not a chemical reaction, chemical change. So the interaction of food with saliva and digestive enzymes. Yes, this is a chemical reaction. It is the making and breaking of bonds. Proteins being broken down into amino acids. Yes, this is also a chemical change. One thing that I always think about is frying an egg. Frying an egg will break down the protein, will change the shape of the proteins, and make it go from the clear gooey substance to the hard white substance. Complex sugars being broken down into simple sugars. Yes, that is also one. Making maple syrup by heating maple sap to remove water through evaporation. No, that is a physical change. That is a good use of separation method, though. It's tasty. DNA unwinding. Oy, oy, oy. This is where we get into what is like a whole lot of technicalities and caveats in this. No, I would say that it is a physical change because no bonds are being made or broken, but there are a ton of intermolecular forces that are being made and broken. So DNA unwinding would be one of those like ones in the middle where it's kind of a physical change because technically nothing is being no atoms are going to be switched, but at the same time so many intermolecular forces between the two strands are going to be broken. We'll get into that in AP for the AP people out there. Okay, so that's enough pre-AP stuff. I've been kind of just focusing on pre-AP for the first bit, and it's 30 minutes. I'm gonna do this. I'm going to take a short break, and then when I do, I'm going to get back into, I'm going to get into mass spectroscopy. So this is going to be for my AP people. Stick around, all you pre-AP people, if you want a peek into what's happening next year. All right, I'll be back in a bit. And back. All right. So, let's go through mass spectrum. Okay. So I found this little worksheet on mass spectrum. We figured we could run through it real quick. The first bit is just how do mass spectrums actually work. So again, we put in our sample of some kind of element, and this is to figure out what kind of isotopes are in that element. You can also use this to figure out a lot of other stuff, the same technology to use, figure out a lot of other stuff about more complex things. But for right now, let's just focus on a single element with a bunch of different ions go through. And so what we do, vaporize it and ionize it, turn it into an ion. These are usually positive ions, right? And then we accelerate them through. They zip forward. And since they're positive, we can use magnets to kind of deflect them. And remember, the lighter things are going to be deflected more than the heavy things. Heavy things are going to be deflected less. So that means we can kind of start separating out the different isotopes based on their mass, how much they weigh, which is exactly what we want to do. And then it flies down and hits a detector. If it weighs a certain amount, it hits the detector. If it weighs too little, it gets banged on the side. Too much, bangs on the other side. And we can adjust this magnet to kind of zero in on things. Now, this goes through and talks about how to calculate average atomic mass. I don't know why they did this. They say to take the percent, multiply it by the mass, sum them together, and then divide by 100. My thought is just do the percentage and make it point, like here, 0.9092 times 220, and then you don't have to worry about this extra step. But whatever, it's the math. It does the same thing. Do it now, do it later. It doesn't matter. And here is an example spectrum of neon. Just looking at this, you can kind of tell that without even doing any kind of calculation whatsoever, it's going to be mostly 20. So, and then a little bit of 21, a little bit of 22. So we can tell if I were to, page is not supported. Okay, fine. All right. So, if I wanted to do this, then I could tell that the actual weight of this is going to be somewhere here. Kind of like in that chromatography lab I was telling you about. Imagine that all of this weights are real on this number line, and then put your finger somewhere to make it balanced. You would probably put it somewhere here, right? This is going to be where you would put your finger. So really close to 20. And if you go through it, the answer is 20.3. But even if you didn't do this entire thing, you know it'd be somewhere close to 20. And if you look on periodic table and look at neon, you see that it is indeed 20. The molecular weight of this guy is 20.1, a little bit above 20. So without this is going to be a shortcut for you if you want to do this without actually having to go through and do the calculations. This is a good way of getting some precious seconds in for the AP exam and my exams, is to go through and look at this and then ask yourself, okay, this is going to be, I'd have to put it about here, so it's around 20. Look on the periodic table. Okay, what's 20? No, 20. A little bit above 20. Neon is the answer. Awesome. And then move on. You don't need to go through and calculate. Here, let's go through this. Consider the mass spectrum for the element boron on the right. Okay, consider it. Considered. Number 1 done. How many naturally occurring isotopes does boron have? In this case, it's pretty simple. You just count them. So there's going to be 1, 2. There are 2 naturally occurring isotopes in boron, at least that we've detected. So then go through, calculate the atomic mass of boron, check your answer, the atomic mass on the periodic table, show your work. So, again, if you want to do a shortcut, you can just look. So this is a 10, 11. Most of it is 11, so I would probably guess it to be somewhere around 11.8 would be my guess. If I looked on the periodic table for boron. Oh, no, I'm sorry, not 11.8. 10.8. So it's 10 to 11, 10.8. And if you look at boron, it is 10.8. But if you want to go through and calculate things, I guess we can do that as well. So we know that it's going to be 10 at this percent and 11 at this percent. So it's going to be 0.187 times 10. Then we're going to add that to 0.813 times 11. And if we did that, we get 10.513. Oh, I messed this up here. Let me redo this. So 18.7 is 0.187. Whoop. Okay. 0.187 times 10. And then 0.813 times 11. There we go. 10.81. Exactly what it was before. Good. All right. So that's how you would go through and you can show your work there. How does boron's atomic mass compare with the mass numbers of its isotopes? What does that mean? What are they wanting me to say here? How does boron's atomic mass compare with the mass numbers of its isotopes? I mean, the mass numbers are 10 and 11. Those are the mass numbers. I guess you could say that the atomic mass is the weighted average of its mass numbers. That would be how I would go about explaining this. That's how I would compare the two. There's a smaller amount of 10 and a larger amount of 11. So the atomic mass would be between but favoring the numbers. Yeah, these type of questions are going to be what you're going to have to get used to, where they just say, how do these guys compare? And you kind of have to do what I just did there. Okay, what are they wanting me to actually say here? And if that's the case, if you don't know specifically what they're trying to say, write as much as you know about mass numbers and the atomic mass if you're not for sure what they want you to say. So that's something you can do. All right, consider the mass spectrum for zirconium. All right, considered. Which isotope is the most abundant? Again, you can just look here. Isotope 90. So zirconium 90 is going to be the most abundant. Which isotope is the least abundant? 96 is the least abundant. Okay. Predict, what will the atomic mass of zirconium be? So again, this is where you kind of have to go through and think, okay, if these are actual weights on a physical line, where would I put my finger? It's not telling you to calculate the thing, just estimate the thing. And these numbers are pretty wildly different, right? So you can just look here. 33.5, is this where you'd put your finger? Well, if you did that, it would probably tip over this way. 92. Yeah, this actually looks a little bit more decent. And then here, 90.5. I'm going to say 90.5. It might actually be 92. I'm thinking 92. Because this 2% is very, very heavy. I'm thinking 92. Let's find out. So we can go through and calculate our things. So 0.515 times 90 plus 0.105 times 91 plus 0.175 times 92 plus 0.185 times 94 plus, ooh, maybe it is 90. Looking at this now. 0.02 times 96. 91.3. So it is going to be 92. Actually, it's pretty close to both of them. It was either 91 or 92. Did I mess up somewhere? One of the good things about showing your work is you can see if you flubbed up somewhere. Doesn't look like it. Nope. Nope. There it is. What is the atomic mass of zirconium? 91.2. Freaking A, man. This is what happens. They tricked us. Neither of these work. None of the answers work. 91.3, I think, is closer to 92 than 90.5. Well, that's like 0.8 away, and the other is 0.7 away, so it is barely closer to 92. So, there's that. All right. What else we got? Lead has 4 naturally occurring stable isotopes. The table shows their masses and relative abundances. How many peaks will a mass spectrum for lead have? So how many peaks are we looking at here? 1, 2, 3, 4. 4 peaks, 4 different isotopes, so 4 different peaks. Draw a mass spectrum for lead based on the data in the table. Wish I could draw on this. Can I draw using this guy? No? Alright. I'm just going to capture this, bring it over here. Nope. Okay. No. All right. Never mind. All right. Draw a mass spectrum for lead based on this data. So what I'm going to do, copy this, paste it here. Insert table. Nope, that didn't work either. There we go. Now I can draw over here. Okay. So if I wanted to draw this thing, I would have a mass number of 204, and this would be 1.4 tall, so just a tiny little thing. And then 206 is going to be further away. If I wanted to actually write 205, I could put it there. And this is going to be 25 tall. So we know that this is going to be 25, and I'm going to call this 50. And for 207, this is 21%, so a little bit lower. And 208 is going to be 52, so a little bit above 50. And this here is your mass spectrum for zirconium. Oh no, lead. This is lead. There's that. Okay. Oh, thanks for hanging in there with me. Challenge! Carbon has two naturally occurring isotopes, carbon-12 and carbon-13. The atomic mass is 12.11. Based on this data, calculate the relative abundances of each of the carbon isotopes. Show your work and give your answer with 3 sig figs. This is just doing it backwards. I mean, he's just doing it backwards. You know, I mean, if you wanted to set up this problem, you can set it up using algebra. Jeez, every time. So if I wanted to set this up, what were the numbers again? 12 and 13, and then 12.011. So 12.011 equals, let's set this guy up, and we know it was 12, and we know the other thing was 13, and then we multiply here, and let's call, instead of using x, because I put x's here for multiplication, I'm going to put z. Okay, I'm going to see how much 12 it is, and then for here, I know it's going to be 100, or I'm sorry, 1 minus z. Because if I added all of those percentages up, it should equal 1, right? So there we go. Now you have this. Solve it. This is algebra. Solve for z. Done. You can go through and do that. I leave that as an exercise for the student. And they even tell you how many sig figs it is, like a chump, instead of having you guys do it. All right, so that's mass spec. I found another mass spec thing, but it is already 2 to 7. So this one's a little bit more in depth. That one was kind of a very general one. This one's a little bit more in depth. One thing to remember is that charge is a thing. Most things, most of the time, if it doesn't mention it, it's going to say that these things are charge plus 1. But you might have something that has a charge 2 plus. Anything in here is probably going to show up as a 2 plus thing. Because this is in our second group, we'll lose 2 electrons here. So there's that. But in this case, they don't actually mention anything, just say mass number, so we can kind of assume that it is a plus 1 charge. How many peaks in the graph? 1, 2, 3, 4. Each peak represents an isotope. Highest intensity is 202. All of this is good. What element could this possibly be? So again, if you wanted to get a quick and dirty one, where would you put your finger? Maybe here. So somewhere between 200 and 201. So just kind of start looking. Nope. Oh, here we go. So somewhere between 200 and 201. So gold is 196. That's not right. Thallium is 204, so that's not right. Mercury, 200.5. There you go. No calculation needed there. That was just very quick. Look at the peaks. Where would you put your finger to balance this? I said somewhere around here. And then go. We already talked about how to do weighted averages. Okay. Label the X and Y axes. So this is intensity, or you can say absorbance, or not absorbance, abundance would be another thing you could say for this. I think it's the term that I've used is abundance. And then here's the atomic mass. You can go through and label these guys. It's going to be 35, 36, 37 is going to be their masses. And then you can figure out the relative abundance of each of these guys. Okay. We know this thing is a diatomic molecule, so if you look at the full spectrum, this is what you would see. These guys over here as well. And this is what we were saying before. I was saying before in class that if you look at chlorine, it's going to be a diatomic molecule. It's going to have BCl2. And if you pull out two balls at random, green and red ball. If you have a big bucket of green and red balls and you pull two out at random, what are the possibilities there? You can have two red, two blue, or I'm sorry, two red, two green, or red and green. Same thing here. If I have two different weights, it can either be 35 and 35, 35 and 37, or 37, 37. And since there's less 37s, we're going to have less 37, 37s. The weight of a 37, 37 is 37 plus 37, 74. So we have a lower number here. Here we have a much higher number because we have a lot of 35s. And if we have two 35s, 35 plus 35 is 70. So our 70 is quite a bit higher. And there's a good chance, but not, there's a decent chance that we're going to get a 35, 37, which would be 72 right here. Okay. And that's that. Real quick, I still see there's a few people that have stuck with me this entire time. Questions, comments, concerns? I'll just kind of sit back on my soda while I wait. No questions. Okay. All right. So I'll say this. I have plenty of videos on my YouTube channel. My AP people out there, we have an exam coming up, a big boy exam. Remember, it's going to be a two-part exam. First day is going to be multiple choice. Second day is going to be free response. These are significant to your grade, so definitely study up on it. I would say minimum 2 hours of studying would be good. More if you are feel like you're shaky on these topics. Next week we are going to be going over photoelectron spectroscopy and then just reviewing how to go from wavelengths, frequency, and energy. All right, that's that. For pre-AP people, if those people still are around, we're going to get into atomic structure. What is an atom? What's in there? And then do a couple of labs next week. So that's it. Hopefully everyone's doing well out there. If you have questions, you know how to get a hold of me. Please do. All right, I'm out. I will see you guys later.